Kidney stones represent a catastrophic failure of physical chemistry, a process known as lithogenesis. Under normal conditions, healthy human urine maintains a stable chemical baseline. This stability is defined by the equilibrium solubility product, the exact point where the concentration of dissolved molecules, like calcium and oxalate, is perfectly balanced by the fluid holding them. When the fluid sits anywhere below this threshold, it is undersaturated. If a microscopic crystal finds its way into this environment, the liquid will actively dissolve it back into separate ions. Healthy human physiology creates a naturally hostile environment for solid rock formations. It is a common assumption that stones form because total levels of calcium or oxalate are too high. However, raw chemical concentration is a poor predictor of stone formation. This diagram shows 100 calcium ions in a fluid, but only the highlighted subset possesses the potential to form a stone. This is chemical activity, the specific fraction of ions that are unbound and free to react. We calculate this by multiplying the total concentration by an activity coefficient. This coefficient accounts for complex interactions within the fluid, revealing the active amount is far lower than the total measured. Standard medical lab tests often focus on total urinary concentration, but without accounting for the activity coefficient, the math is insufficient to predict when a stone will actually materialize. When the active ion product crosses above the equilibrium solubility product, the fluid enters a state of supersaturation. In this state, existing crystals will grow, but new crystals do not spontaneously appear. This creates a precarious gap called the metastable zone. Metastability is a highly volatile holding pattern. The liquid carries a heavier payload of dissolved solid than the laws of physics should allow. This delay exists because of an energetic barrier. Creating a solid crystal out of nothing requires a massive expenditure of free energy, forcing the chemistry to stall. Human physiology relies on this delay to survive. The system exists like a stretched rubber band, loaded with tension and waiting for a trigger to snap. Managing that tension depends on how the kidneys regulate the urinary environment. Increasing urinary volume acts as a primary defense. By expanding the fluid denominator, the body physically pulls the saturation ratio back down toward the safety of the solubility line. Complexation provides another layer of physiological control. Natural inhibitors like citrate hunt down and bind to calcium, disabling its chemical activity and preventing it from reacting with oxalate. Finally, the body actively manages urine pH. Microscopic shifts in acidity reorganize solubility ratios, determining whether compounds like phosphates and urates stay safely dissolved or begin to precipitate. Effective dietary treatments for kidney stones specifically target these biological mechanisms to relieve metastable tension. If volume drops and inhibitors fail, the free ion activity product surges upward without resistance. On the chart, the fluid surges past an absolute thermodynamic ceiling known as the formation product, the upper limit of metastability. The environment is now unstable. This triggers homogeneous nucleation. The energy barrier collapses, and entirely new crystal nuclei spontaneously snap into existence directly from the fluid. Crossing this threshold marks the moment liquid chemistry transitions into solid geology. Once formed, these microscopic crystals use the surrounding supersaturated liquid as fuel, pulling ions from the water for rapid, uncontrolled structural growth. Electrostatic attraction then forces these charged particles to crash together. They coalesce into massive, jagged networks in a process called aggregation. This microscopic chain reaction is what eventually leads to a physical stone lodging in the urinary tract. Preventing this disease requires the deliberate management of your own physical chemistry to ensure the system never reaches the upper limit of metastability.